So this is what that we have discussed last week. The principle of sensor, regardless of biosensor, physical sensor, or chemical sensor. And this one, to remove the drawing. Okay, so I hope that you remember. Okay, so the analyte, just to recap, the analyte is the one that we wish to detect, whatever it is. And previously, I have given you an example of oxygen in blood, where you use smartwatch to check the oxygen level. And I have given example that the diamond shape just now here, let's say it is oxygen in the blood, okay, and they are interacting with the receptor. You can see that only the diamond shape is interacting with the receptor, okay. So the receptor interacted with the oxygen in the blood, which is the analyte, will give in some signal changes. Yeah. So these signal changes is detected by transducer. So I think we have discussed the transducer can be optical. An example of optical that we use that you are probably familiar is UV, fluorescent. So what happened is when the oxygen interact with the receptor, okay, there is a changes in terms of wavelength, colors, fluorescent intensity, which is detected by the transducer. Okay. It can also be electrochemical technique where the interaction between the analytes, in this case oxygen, react with the receptors, producing changes, and there is a current change, for example. So this is the basic that I discussed last week. And the final part is the signal. We don't want to have the signal in a form of current, or we don't want the signal to be in a form of curve or reading of wavelength, because we want the final result to be directly customer friendly. For example, you want the oxygen in 98% or 100%. Okay, those are the things that public or the users wants to read. We don't want to calculate or do some calibration whatsoever. What we want to have the final result. So in order to do this, we have to do some software programming to convert the reading to auto calculate and so on. So that's why we need to have experts in development of sensors, not just chemists, not just biochemists. We need to have more than that. Yeah. So this one is last week, and I have given you the smartwatch example, and we have discussed some difference in terms of general difference between antibody, aptamer, and DNA. So these are, for those who are new here, these are what we call as receptor. Example of bioreceptor. And I hope that you have at least have a look at DNA. Okay, of course, you don't need to go into detail, but at least understand the structure of DNA, especially the nucleic acid, the bases. Okay, So the structure of nucleic acid, this is the bases, and we have the phosphate backbone and the glucose. Okay, so this is the basic structure of the DNA. It can be single strand. Single strand, if you just cut this into two, you get single strand. If they combine, you get double strand or double helix DNA. Okay, so that's the basic. And how they interact. Okay, I told last week about the A. It will be matched with T, adenine, thymine, C, cytosine, and G, guanine. So it has to be, the pair is that way. It will not, there will no interaction between A with G or C with T. Yeah, it has to be with A, T, C, G. So the interaction is through hydrogen bond. So because if you understand the basic structure of nucleic acid, they have amine and they have carboxylic. Yeah. So these are the basic structure, chemical structure of nucleic acid. Okay. So not complicated at all. It's just you need to understand some basic structure, because in order for you to understand the how it works, how do you use DNA to detect or to build out biosensors. Okay, so that's why I need you to from 8 to 9 after this is for you to spend your time in looking at the video, because it is animated video, which is more, is friendlier, is more can be more interesting to understand the concept of DNA biosensor. So if you wish to just look at other YouTubes as well, there's a lot of other YouTubes that gives you more understanding on the biosensor, DNA biosensor, yeah? Particularly DNA biosensor. So I've given you an example before that, let's say now I have called for more than 2 weeks, then let's say the doctor asked me to test for tuberculosis. So let's say my sputum is given to the hospital, and they will test, let's say they extract from my sputum a sequence of DNA, okay, DNA, and they already have what we call as a specific sequence of Mycobacterium tuberculosis. So I don't want to write here Mycobacterium tuberculosis. Yeah, I'm giving you the real example. Tuberculi, the name of the bacteria that cause tuberculosis. So they should have the specific sequence that represents, meaning that the DNA confirm the existence of Mycobacterium tuberculi. Okay, so if they extract DNA from my sputum and react with the sequence that they have, and if they have a perfect match, okay, this will indicate that I am positive TB, for example. I have tested before and I'm not. I have to submit my sputum every morning, 8 o'clock. Imagine that you have to really go through all the traffics and give your sputum to the hospital for 3 consecutive days. So that's how it is. But if you have a sensor at your home, then it will be very easy. You don't have to really fight your way in the traffic to go to the hospital. So if the DNA here is a perfect match with the specific sequence that they have, then as I mentioned just now, then you are TB positive. Okay, so let's say if we have like mismatches, 50% mismatch, okay, 70% mismatch, then it is subjected to further study. Okay, That's why DNA biosensor usually sensors. It is more on monitoring. So if you have like a suspicious being positive for TB, but the results is not that clear, then you are subjected to further investigation. So now the issue is, how do you know it is 100% match or 50% match? Because DNA, or what we call, when this DNA match with the specific sequence, it is called hybridization. Yeah, this is the word, nucleic acid hybridization. When the single strand from the sputum, it is react the specific sequence that they have called probe, they react and form a double strand DNA. The process is called hybridization. Yeah, this is the one that we have. So this is a perfect hybridization, and it is a perfect match. So in DNA biosensor, we have to design, okay, how to detect whether it's 100%, 60%, 70%. Remember about the this one, yeah? So now I'm asking you, what is the bioreceptor here? Anyone? What is the bioreceptor here? Hello? What is the bioreceptor that we are using in the DNA biosensor? Am I the only one here?
Nobody.
Yes, Ahmad?
I'm not sure.
You're not sure.
It's the DNA sequence,
Yes.
Prof.
It's the DNA sequence. Okay. So because that's why this is the basic, like I have told you before. So the one that catch or interact with the analytes in biosensor, in DNA biosensor, is itself. Okay. So I need you to relate this with the picture of principle of biosensor just now. Okay, principle means that here. Yeah. All right. So now, when we are referring to DNA biosensor, the receptor, we are using DNA as the receptor. And for the tuberculosis, we are using DNA that is specific to the Mycobacterium tuberculi, because we want to check whether there is Mycobacteria tuberculi in my sputum, for example. Yeah. Okay. So, right. So now the next issue is, what is the transducer? Okay. The receptor is clear now. Okay. The analytes. Okay. Let me. I'm not good at it. This cut. Oh, yeah. Okay. Okay. The analyte. Yeah. We want to detect the Mycobacterium tuberculi, because that's one we want to detect, the bacteria. Okay. And number two, the receptor is the DNA, because the hospital, for example, has the DNA sequence that is specific to Mycobacterium tuberculi. They have it. I mean, it has already been designed. And this is what we call as probe. Yeah. Usually the name is probe. So get used to it. Receptor DNA name probe. Okay. Now, the third one, okay, the sample that is submitted is sputum. Okay. So this is just to complete the story. So sample sputum is submitted. So we want to know whether in the sputum contain Mycobacterium tuberculi. we run the analysis using a receptor, DNA, which is specific to Mycobacterium tuberculosis. The issue is whether we get 100% hybridization match between the DNA from the sputum with the receptor, or we only get 50%, or it's no match at all. How do we detect that? So that is DNA biosensors. Okay, so now, okay, it's supposed to be, okay, let's look at the colors first. Okay, so now you have 2 green here. Okay, imagine that all those green and red, they are DNA. Yeah, they are DNA. So the green one, okay, the green DNA, imagine that they are the receptor. Means that we put it on the sensor, or the probe that is owned by the hospitals, which has been designed to represent Mycobacterium tuberculosis. Let's look at it. Okay, and the red strand, red strand is from the sputum. Okay, okay. So this is probe, green one. And the red one is from sputum. Extracted, it has to be extracted, okay? So now, if you mix it, okay, you just imagine a beaker. You don't want to imagine all this because this comes later, NH2, silicon nanowires, okay? You just imagine a sputum, a beaker, where I put the extracted DNA from sputum. Let me add another slide. Okay, blank. Okay, so you have the, okay. So now you have the beaker where I put the DNA from the sputum, And inside here is the probe DNA, which is already established as indicates the Mycobacteria tuberculosis, Okay, all right. So now, in order to know the perfect match, or it's not a perfect match, okay, I have to add another one. Insert. Okay. So just now we have a few colors. Green. It's not green. Okay. So this is the DNA probe. And rates from the sputum. Let's say they match. They interact 100%. Let's say. So this is green. This is green. They have perfect ATCG interaction. Okay. So in order for me to know how much the hybridization, so in here, I have to put some indicator. Okay. So here I have to put some indicator. Yeah, probably too complicated for you to understand. No, it's not that difficult. With the solution that contains together all this, and this indicator will interact with this DNA hybrid. Okay, so that's what you see here. You can see the green one is the probe. The red one is the DNA from the sputum. and then we mix with indicator. So this indicator will indicate, that's the purpose, will indicate how much the hybridization happened. So if you see here, this is the transducer. So in this case, the transducer is conductometric. Okay, so I hope that you understand when I say transducer, because I have presented to you transducer. So transducer will show, will translate the interaction into signal. So you can see here, if there is only green one, yeah. Oh. If there is only green, because I haven't put my sputum at DNA extracted from sputum in the beaker, okay, you can see this is the reading. Okay, means that there is no interaction yet. So it's a basic reading. Now I start to put my DNA from the sputum, and they start to interact, forming a double helix structure. It seems that it has 100% match. And there is an indicator that I have put into the system. And this indicator will result in the changes. I put here changes here in terms of conductance. Okay, so as the transducer is the one that we are using right now is conductometric, means that there is a change in terms of conducting characteristic. You can see that after the interaction, there is a changes in terms of reading. Okay, so here the changes is translated into a current. So the one that give you the reading here resulted from one, the interaction between these, okay, and plus the indicator. Okay, because this indicator will give out changes upon interaction with the hybridized DNA. So you can see that one, you have receptor here, and then you have the analyte, supposed to be the analyte, because this is the DNA from the sputum. They interact, and how to get the signal from this interaction, we need to add another indicator. This depends on the transducer technique, whether we are using optical or electrochemical. So if it is optical, we might be using some indicator that have color change, just like pH indicator, okay, for example. So in this case, we are using conductor. So the indicator is sensitive to conductivity. So in this case, it is translated in the form of voltage, current, okay? So there are many types of indicator. We are not going to discuss indicator now, but for you to understand at this stage, why am I not moving? Is how it works. Understand, just understand first. Okay, so from 8 to 9, you need to watch the video. It's an not interactive, it's animated video, so at least you understand. So you can just also watch any other. You can just type DNA biosensors animation, and that will help you to understand. Okay, questions?
Prof,
Yeah.
for the conductometric, so if the change of the current is less or not significant, so do we say that there's a mismatch or not perfect hybridization?
Yeah, very
Something like
good.
that.
Yeah, that is the key to the how we decide on 50%, 70%, because we validate the system first. We design it to be, let's say when we design the sensors, let's say we design it to be 50%. We know already, because usually when we start to work with development of sensors, we work with synthetic samples. We don't work with sputum right away. We call it not from real samples. So if we are working with synthetic samples, we can design it to be 50% match, 70% match, or whatsoever. So from there, we validate, okay, the current change is due to 50%. The current change is due to 20%, for example. So yes, that is the how we read the percentage of the hybridization. Okay, one last slide. Okay, so this is an example of what have been done. Okay, I'm not going to bore you, but this is the construction of the DNA biosensor. Okay, so now there are few things that really has to be studied. One, okay, remember about the receptor, of course. So here the receptor is DNA, okay? But the issue is, how are we going to put the DNA, the receptor DNA, onto the sensor, okay? Or the transducer. So this is, let's say, this is the transducer. I put it in box, okay? You just imagine it is a box. And how do I put the DNA receptor here? Okay, so that is one issue that we need to solve. That's why we are going to learn the immobilization technique. That is what immobilization techniques for, because you need to know the chemistry, the right chemistry to attach the DNA receptor. So that's why when we learn DNA biosensor alone, we have to go step by step. We need to learn about the attachment of DNA first. And then we need to know the right indicator. And then, of course, the transducer. Okay, now, so we are going to learn the chemistry here. And also, here is also the chemistry, because chemistry, you cannot just put anything on top of a transducer. Yeah, I mean, if you have transducer that is silicon, for example, okay, silicon, it does not behave similar if you have a transducer that is gold. So gold surface have different chemistry compared to silicon. So we need to have a right chemistry in order to attach DNA receptor on top of silicon. Or we choose to have gold, then we need to know the right chemistry to attach DNA on gold. So the chemistry of attachment of the receptor is very important. Okay, so if we those are doing sensors fail to understand the chemistry of the material, transducer material, and the chemistry of the bioreceptor, then the whole thing will fail. So this is the fundamental first. And then the next process is, of course, the red one is imagine the DNA from the sputum. Now it has to interact with the DNA probe, specific for the Mycobacterium tuberculi. And then you have indicator here. So this is an example of indicator, methylene blue. Okay, we will discuss what types of indicator that works for DNA. Okay, and then when they interact with the hybridized DNA, so you have a signal generation. Okay, let's say before interaction, and this is after interaction. So you are correct. So the difference of current will indicate how much hybridization. So one thing is yes or no. You want to know, okay, you are positive tuberculosis or you're not. The other one is based on how much. Okay, it can also indicate for example, if you have dengue, there are other variants. Okay, there are 4 serotypes of dengue. So even though it's not important for us to know which serotypes of dengue is infecting us, but sometimes the percentage also very important. But this is not something that I want to discuss here. Okay. So this is an example using electrochemical technique. I'm just giving an example because you haven't learned about electrochemical technique yet, but this is the whole process. Okay, so I hope that you can go through. Okay, this is via, why it's not moving? Okay, so this is different types of transducer, fluorescence. You can see that it is also based on hybridization, but it is the parameter that we measure is based on lights, is based on intensity of lights, fluorescence. Okay, so this is just an example. I'm going to discuss this later, so you don't need to worry about this. Yeah, I'm just giving an examples of different transducer used in the biosensor. So this is fluorescent, okay, and these are also other types of transducers. Okay, all right, okay. So please do as I instructed just now, please do watch DNA biosensor first. Especially those animated videos. So I have given some examples of animated videos in the Putra Blast, which is developed by the previous students, which is good. But you can also watch any other YouTube videos so that you understand how it works basically. Not to the extent that you can calculate whatever, but you understand. Before we move on to immunosensors, because immunosensors is based on antibody. Okay, everybody can do that.
Okay,
So
bro.
8 to 9, no class. You just watch the videos. Make sure that you understand. You can catch up with the basic principle. Okay, everybody, enjoy your break. Thank you and bye-bye.
Prof, thanks.